Welcome, everybody. Welcome back from lunch. We have some more people coming. Appreciate you making it here to this session. Maybe it was my title. Let's see. I want to make a call out. There's at least one person that attended my BRK 1005 last year. Thank you for coming back. I hope you will not be disappointed. And also thank you. There are a few people that have been at the tutorial on Sunday for routed optical networking. Also, thank you for coming back, assuming that you're in the room. I don't know. I only saw the registration, so I didn't. But I think I see some faces. So, a few words on myself. My name is Christian Schmutzer. I'm from Europe, which you may hear from my dialect, as well as also see from my name. I joined Cisco quite a while ago. I was much younger. The people that are thinking that they're older than me probably question themselves, how young was this guy when he joined Cisco? But I joined directly from university. I really appreciated that I joined during that time because I had the chance to learn MPLS when it was still called tag switching, which was really an amazing and exciting time. And also, during that time, Cisco invested quite a few money in buying a lot of optical companies, and we started getting active in the optical space. And being a system engineer in Austria, small little country, used to be big, but now very small, I had the honor to actually start looking at this optical stuff. And essentially, from then onwards, I started not only learn IP, but also optical, which in hindsight, I think was a great thing, actually the best thing professionally that can happen to me, because I think being able to understand both worlds is a pretty unique value add that you can bring to the industry. Now, a fun fact, I would say most people, or many people, follow the money. So they may start in engineering, go to sales, and think they become rich. I probably don't understand this point, so I'm going the other way. I started in sales, went to the marketing organization, supporting as a TME a bunch of routers, and nowadays I'm looking at new technologies, mostly a mix of optical and packet, and are becoming more and more engineering focused. And if I don't work, which I don't work all the time, I enjoy riding a motorcycle. This is my nice KTM in the island of Sardinia. I just came back from there, beautiful island. If you're a motorcycle rider, I can only recommend going there. If you like beautiful beaches, it's also a very good spot. We have a WebEx space. You have seen this slide. Honestly, if you have any questions, I'm here until Thursday, kind of late, early afternoon, so you can pick me anytime or send me an email. My email address is later on in the slide as well, or ping me on LinkedIn. But if you have something to talk about, please try to reach out to me. In person is much better than via the electronic form. So just to put the session into perspective, and I think the slides are on the WebEx, on the events application, so you may have had a look. So maybe you get a little bit of a sense what I'm going to talk about. But just to set the stage, I'm not questioning the use of using multiple wavelengths to increase the capacity over an optical fiber, right? I'm not questioning DWDM. I'm also not questioning the use of optical routing, optical switching, or reconfigurable ODMs, right? They have their place, and we use those two technologies in order to get the most out of our fiber infrastructure. However, what I'm trying to stipulate here and question, do we still need, at the electrical layer, something between the routers and switches and the photonic layer that does mux bonding, TDM switching, right? Being it OTN, SONET, I don't think we have to question SONET anymore. That time is gone. But the question is really, do you need big OTN switches? And do you need a pile of mux bonders in order to build an optical transport network? Now, we have been using them for a reason, right? TDM technology is giving me a circuit-oriented way to deliver a service, an end-to-end, point-to-point service with a particular bandwidth, because the time slot does not only establish the connection, but it also has a certain capacity associated. So when I establish the time slot or the sequence of time slot cross-connects, I also give bandwidth to my customer, and people love that. It gives me embedded OEM, right? The OTN technology is defined with a lot of overheads and bits and bytes that I can use to operate the network and understand what's going on. And the nature of being able to agnostically map anything into an OTN time slot or ODU is very beautiful, because I can carry not only Ethernet, I can carry OTN inside OTN, I can carry SONET inside OTN, I can carry fiber channel inside OTN, I can carry video, whatever you can think of. So really a bunch of good reasons for doing so. Now, what I'm trying to say is, though, the time has changed, and a lot of things have happened in the IP and MPLS world, and we can now actually use a connectionless network using two new categories or two new technologies in order to do or achieve what was not possible before. In the transport side of the house, we can use a traffic engineered paradigm. And by the way, circuit-style segment routing introduces a traffic engineered paradigm for segment routing. It's not the only choice. Of course, you could use classical RSPTE. But really, I would say some of the characteristics of circuit-style segment routing really make it now something that you can easily use to achieve the behavior. And then private line emulation, a new concept of circuit emulation that gives me the bit transparent and payload agnostic mapping of anything you can think of into packets. My personal project for the last couple of years basically fills the gap here that I can not only carry Ethernet, but something else as well. Now, for those of you that have not looked at the slides, I have to disappoint you. This presentation is not going into detail of private line emulation nor circuit-style segment routing. If you are interested, I think my presentation in Amsterdam at Cisco Live has been pretty good in giving you details, including also some live demos, and there is a recording, right? So this session was really, focused around giving you the technology details. What I'm actually trying to focus on this time around is things that I didn't have time to talk about, because I only have 60 minutes, right? And if I want to cover in 60 minutes the technology basics and some of the whys and why nots, it's just too much, right? So my focus here is a technical presentation, but really about more of the motivation, right? And also what I'm trying to share with you is some of the concerns I have repeatedly heard. And there were some discussions with customers and people were basically, hey, I need lowest cost, I need low latency, I need guaranteed bandwidth, and I cannot get that, right? Really what I want to try to do here is kind of a chart, of the top 10 things that I have been hearing and I have been addressing. By the way, if you have any question, please interrupt me at any time. That's perfectly fine. So number one on the list. Some people may have deep pockets, some people may have not deep pockets, but even if you have deep pockets, you probably want to optimize your cost, right? So let's have a look at this. That's kind of the, changes, a lot of changes have happened, and in the area of cost also a lot of things have happened, right? A lot of innovation has been driven into the Ethernet or packet switching world, right? I mean, there's probably, thanks to the web scalers and the appearance of cloud, essentially our packet switching silicon has grown bigger and bigger and bigger, right? We now get 50 terabit ASICs, we get 100 terabit ASICs. We actually have ASICs that are way too big than we typically need them in a lot of cases, right? If you look at that, what happened in the TDM world, nothing happened, right? The innovation really stopped roughly 2015, right? The biggest framer you get from an OTN side is roughly a terabit, right? Depending on how you count the numbers. There is maybe another one coming up. I have met with the predominant vendor of that framer. But really, even if that comes, you double that up to 2 terabits, right? We're still somewhere here. We're not on that exponential curve, right? And if the chips are bigger, overall the cost will be driven down. Also, a lot of innovation has happened in the past. DWDM interfaces were big, clunky, and now we get them in pluggables. I don't want to dwell on that too much. I think we have been covering this for a long time and in a lot of sessions here on that conference as well. So really, it's now very easy to build a router that's cost-effective and even has an optical interface that spits out a specific wavelength. Now, we're also building routers differently, right? A lot of integration has happened, right? I mean, back in the days, we built cards by putting more and more chips on. And I remember when I started joining the business unit, we just built a 10 gigabit card for the Cisco 7600. Anybody remembers this box? Okay, cool. So we had the 10 gig card, and then we built the 20 gig card. So what did we do to build the 20 gig card? We just put twice the amount of stuff, the same stuff, but twice of it on the same card. And that was as much as we could do, and we barely could do that. Nowadays, the chips are so scalable, they have everything inside. Honestly, a card, I mean, I don't want to undermine the efforts and the excellence that our hardware team is doing, but basically you take a line card, put a bunch of chips on it, then put a bunch of holes for SFPs, QSFPs, that's it, right? Oversimplified, right? But back in the days, you never had the right chip, it was never big enough, right? We also started building routers differently from a physical orientation, right? In the past, we had backplanes, and then we had line cards and fabric cards, right? If you build a router back in the end of the 90s with a CPU and a bunch of megabits, the backplane was not the big problem. But those backplanes have been becoming very sophisticated. I mean, the ESA 9000 backplane is a big beast of a backplane, right? And it comes with a price. So at some point, people said, well, why do we need the backplane, right? Can we directly connect the line cards and the fabrics? And yes, orthodirect approach is nicely doing that. And funny enough, if you now look at the router, and there is no fabric card, no line card in it, you can look through it like through a window. There's nothing inside, right? I mean, there's power supplies and fans, right? But, nothing, right? It makes it simpler and easier and more cost-effective. And then, I didn't know that for a long time, that actually air is used to cool, but air doesn't like to be bent, right? If you have the backplane, you have to send the air around it. And with the NCS 6000, somebody remembers? Right, it was a special, we were really proud, hey, we had an optimized airflow and it was very efficient, but still we had to bend the air around the backplane, right? If you don't have to do that anymore, because you now can actually blow the air through the holes of the front card, along the card, along the fabric, and then just through it, it's much, much easier. Another thing that I wanted to point out, did you actually know what's inside an OTN switch from various vendors? I'm not specifically picking up on the vendor. You have OTN framers, and then you have a cell-based fabric in between, right? Now, that cell-based fabric is more or less a full-fledged router. It's like an NCS 5500 inside the guts of an OTN switch. Now, an NCS 5500 in the first generation was probably not as feature-rich as the ESA 9900, but it is a router. It can route packets, right? And some of the characteristics of that fabric that spits out cells or transfers cells between the OTN framers is really what we have now with the current routers that we're using. So if you don't have those framers, obviously, less chips, less cost, right? So this may sound all nice for you, and you're asking, what does this really mean? Let me try to put all of that together in an abstract way on a timeline. So 2014, this was actually when I started looking at packet optical technologies. A vice president asked me, hey, can you join the optical team and kind of look at adding packet capability to that system, right? And I started looking at this, right? And at that time, our routers were roughly twice as expensive as OTN switches because we kind of had very complicated routers. Now, over time, the routers became cheaper, but with a next generation fabric and new framers, also the OTN switches got cheaper, right? But the gap was closing. Now, fast forward to 2025, really even more innovation driving the cost down of the routers happen. And I would contemplate routers are now cheaper than OTN switches. And they are cheaper or equal cost than if you use Mach sponders, even in a back-to-back kind of fashion, to implement some kind of electrical muxing and switching, right? So what I'm trying to say is that with all of this history, using routers, you actually can deliver a network with low cost. Next one, latency. Show of hands, who is concerned about latency in an IP network? Okay. Actually, I forgot to ask one question. Who is running an IP network? Okay. Who is running an optical network? Okay. Who is running both? Okay, so it's kind of an overlap. Okay, good. So, latency. Of course, everybody's concerned about latency, but here is a table I found in a paper written by a company that no longer exists because they got bought by another company. It doesn't matter. I'm also not trying to kind of badmouth that company, but I think that table I really like. The paper was about how to build a latency-optimized network, right? And they're basically listing a bunch of things, and I want to start with the bottom one, right? Routers are slow, milliseconds, right? And I have come across this, and that's why I was trying to get a sense of the optical and IP focused, right? But in a lot of meetings, I got basically into a situation where people said, oh, the routed network is creating all these milliseconds and all this latency, and you can't do that. I need to use bare bones optical transmission technology to get lowest latency. So let's have a look at that. Yes, once upon a time, we did only CPU-based forwarding. A packet comes in, we have a CPU making the decisions, we store the packets in the memory, in a DRAM, like our PC. I mean, literally, I would actually see the Cisco 7000 probably was less powerful than this thing, right? But this was a router, right? Obviously, you have latency, right? Nowadays, routers have a control plane and a forwarding plane. They're separated, and the forwarding plane is hardware-based. So you have MPUs or ASICs that forward the packets. They store the packets in internal or external memory. It doesn't matter. The external memory has a high capacity and is very, very fast as well. So you roughly see 3 to 10 microseconds, right? Depends on the router, right? Is it a pizza box? You have only one ASIC. Is it a bigger modular box? You probably have like 3 ASICs you have to go through. Depending on what the ASIC does, you may have a little bit of latency, but give and take 3 to 10 microseconds, right? Now, yes, there is some additional latency coming into the picture, right? And that comes from the nature of packet switching being connectionless, right? And we can have the situation even in a non-oversubscribed network. For example, 10 gig ports send packets to a 100 gig port, no problem, right? Overall, you will not have any latency. Nothing is getting really buffered, except if at the exact same time, multiple packets want to go out to the same port, right? Because at a particular point in time, at the nanosecond, we can only send one packet or one sequence of zeros and ones as it appears on the fiber, right? So naturally, if we have multiple packets at the same time coming in on various ports, we have to decide which one to take first, and the one that comes after basically have to wait until the other packets are getting sent out. So this head-of-line blocking nature of packet switching introduces some delay, which is variable because it always depends on, am I a packet that has to wait for 1 or 2 packets, or am I a packet that was lucky because nobody else wanted to go out on the destination port, right? And that actually also somewhat translates to the minimum buffer that a switch or a router actually has. So let's look at the numbers here, right? Let's maybe take the dark blue line. If I'm a packet that has to wait for one packet to be sent before me, on a 100 gig port, it takes 0.7 microseconds, right, to clock out a 9,000 byte packet. If I'm on port 10 and I have to wait for all the other 9 ports to send out their packet, I have to wait roughly 7 microseconds, right? So you see the variability. And I have done some extensive testing a couple of years ago, and essentially for me, the summary is, through a router, you see roughly 3 to 10 microseconds of somewhat constant intrinsic delay, and you see plus minus 5 or 10 microseconds of variable delay, depending on this fact that whether you need to wait as a packet or not. And of course, the numbers change with the payloads, with the packet size, as well as the interface speed. The smaller the interface speed, the longer it takes to send a packet of the same size. The bigger the packet, the more time it takes as well. Okay, now there's another thing, which actually is the truth, right? If you have an electrical muxponder or an OTN switch, you're gonna roughly see 10 to 100 microseconds of latency, right? Now, I wanna share a fun fact. We talked about the cell-based fabric between the OTN framers. That cell-based fabric is basically passed across by the OTN framers to do some kind of emulation, right? The bits or frames are getting packetized or split into cells and then sent across with some variability. So you have to have a digital buffer to ensure that you can actually reconstruct your frame. And that digital buffer has a certain amount of latency. And that's why you see roughly 40 microseconds through an OTN switch, right? Now, we just talked about routers have 3 to 10 microseconds, right? I'm not trying to make here, so to speak, a speed contest, right? All I'm trying to say, routers are not really slower than OTN switches, and whether they're equally fast or slow, we can it doesn't really matter, but we are in the same range of microseconds. Brings me to the last point. The most important point in this table is actually the basic propagation delay that you have through the optical fiber. It's roughly 5 microseconds per kilometer, right? So what I'm really trying to say here, you can argue all day long about which box is introducing more latency, right? If we talk about building a wide area network, spanning a certain area, and I was trying to make here a little bit of a local example. Honestly, I put the dots here without any knowledge of San Diego. Is there anybody from San Diego here? Okay, so I apologize. I just wanted to build a ring on a geographic map, okay? And I'm just saying we have maybe 2 core or hub sites, and then a bunch of access sites, and you may want to have a connection between those 2 locations. And I know there's many ways you can build a network. Just as an example, if I would have a muxponder in these 2 locations and I terminate the wave on those 2 locations there towards an OTN switch to have central OTN 10 gig grooming and the ability to efficiently mux and demux or switch my 10 gig services over 100 gig waves, you could build this the way I show it here, and then you would see 200 microseconds just fiber latency, right? And under the assumption that the same customer may have needs for packet switching in all these locations, right? If you can buy routers that are cost effective and fit your needs and you place them there, in order to connect the two endpoints of the customer, you can use the optimum route on the top and you have roughly 100 microseconds, right? So don't take that as an exact example. I'm just trying to prove the point. Can you actually deploy OTN switching always where you want it, or are you, because of cost reasons, of space reasons, deciding not to put it where you maybe need it? You may end up actually geographically using or routing your traffic not in a geographic optimum way, and that actually introduces quite a lot of latency. Okay. Next one on the list, bandwidth. So if I have a time slot that has a certain capacity associated, nobody can take that capacity away. It's pretty simple. Everybody's happy. It's this notion of, the time slot belongs to me. Nobody can steal it from me, right? In the packet network, you don't have a time slot that is nailed up, right? So a lot of people are having the concern, this packet network may do strange things, right? I cannot guarantee bandwidth to a customer. But in the end of the day, if you know where your traffic flows, and if you plan for your traffic flows, and you run your network for certain traffic classes in an non-oversubscribed manner, there is no reason why you cannot guarantee bandwidth to a customer. Now, know where your traffic flows is probably the tricky part, right? If you just use standard IGP routing, basically packets just flow through the network and you don't have really good control. Segment routing is giving me one very great tool in the toolbox here. It's called segment routing traffic engineering, or SR policies. And what I can do with an SR policy, I can map traffic onto it, and the SR policy towards a certain destination has what we call segment list. And that segment list encodes in the packet header what the path of the packet shall be through the network. Let me make an example. We have a network, I want to send traffic from A to Z, right? Segment routing, by the way, anybody familiar with segment routing? Okay. For the other ones that didn't show the hand, segment routing is a source routing principle, right? What that means is that in the packet header, we instruct the network by adding one or more segments. In the MPLS case, it's labels. In the IPv6 or in the SRv6 case, it's an IPv6 header. And we use that information in the packet header to instruct each and every router to forward the packet in a certain way. Now, if I put 3 segments on the packet, each of the segments representing the so-called adjacency set of the links that I'm highlighting here in blue, I'm essentially from A, by defining the packet header, exactly determining how the packets will go through the network, right? Because if router number 1 receives a packet with the first adjacency being the segment for the link, it will send out the packet on that link and not on any other link. So it gives me a deterministic way to forward packets defined from the source. I don't need to do some fancy or complicated policy-based routing in the middle of the network. From the source, just by constructing a packet header, I have the total control how the packets flow through the network. Now you would probably be questioning, okay, this sounds cumbersome, right? If I need to always configure those segment lists, who's gonna do that, right? Now, we're talking here about bandwidth, right? There's 2 things. How can I decide the segment list, and how do I actually understand that my network path has the bandwidth? The answer is the centralized path computation element. Think about it as a routing intelligence in the network centrally that knows the topology, right? So if you configure a policy to be used for your service, the source and destination will request from the centralized path computation element, hey, I want a path from A to Z and from Z to A with 10 gigabit. The path computation element will find the suitable path, will construct the segment list, and send the segment list back to A and Z, and then basically packets will flow, right? With this, we can easily achieve what I just mentioned before. We understand where the traffic flows, and we keep track of the traffic so that it does not, go over what we have. Now, still a lot of people say, how can I really be sure, right? But honestly, if you have 2 simple rules here, one, that if you want to guarantee bandwidth, you put traffic in a SR policy, and you make sure that whatever service uses that policy, on aggregate, will never send more as the configured or requested bandwidth, and you make sure that that policy traffic is never gonna get dropped during congestion, you're good, right? Now, how can we ensure that that traffic is not getting congested? Well, the first thing is, don't commit what you don't have, right? Essentially, keep track of your policies in the network, and that's what the centralized path computation element is doing, right? You fill up your network. I'm showing here a link with a subset of the bandwidth being associated, right? And if the link is full, use another link, right? And on top of that, mark your packets so that they have very high priority, right? And in the most simple term, basically use the highest data priority. And I'm saying highest data priority. Of course, network control should be higher. But network control, in the grand scheme of things, will not be a lot of bandwidth, right? What you really are worried about is the data bandwidth. But if you use a higher priority, whenever you have congestion, everything else will get dropped, and your guaranteed bandwidth traffic will not get dropped. Okay. So, co-routing. In optical networks, we always have this request for traffic being co-routed. Now, I would stipulate the reason for that is unclear to me. I would say potentially because back in the days, especially in the US, where SONET was basically Turks controlled, you had this like hop by hop troubleshooting, and it was easier if you follow one path to know that the reverse path is on the same way, right? In a packet network, do you really care whether traffic flows in both directions along the same path? Questionable, right? But if you want to do that, we can do that also with circuit-style segment routing by simply combining two segment routing policies into an association group, and we basically say, you are the forward and you are the reverse, and you belong together. So when we do the path computation, we just say, hey, these guys belong together, compute them on a co-routed path across the network. Plus, you're gonna potentially look at bandwidth and whatever, right? As simple as that. Now, maybe at that point, it's a good thing to mention, circuit-style segment routing is not a new technology. It's more or less a set of existing SR capabilities put together into a solution. And we have been working with several vendors at the IETF to standardize this solution, if you will. The document is pretty well ahead and should hopefully soon become an informational RFC. Well, as I said before, do you really need that, right? I think there are some very good reasons for asking for co-routing, right? And one of them is potentially, hey, I want to have equal latency, right? Now the question is, why would you actually have, asymmetric latency in your network? Potentially, what could happen is that if your network has multiple paths, right? So multiple equal cost paths from a hop perspective or IGB metric perspective, you never know where your traffic goes, right? So it may be helpful to say, hey, we're gonna pick that, zigzag path here because that one has significant different latency to the other ones, and I wanna make sure that both directions use the same one. I think that's one of the use cases. Having said that, IGPs now, or with flexible algorithms, I can actually say, I wanna run a service over a flexible algorithm that looks not at IGB metric, but at latency, and then you can achieve more or less the same thing, right? So it's up to you if you want to do that or not. Okay. I'm actually doing good on time. I'm impressed. Protection and restoration. So you see here a common theme, right? Essentially, circuit-style segment routing is pretty much dealing with the packet behavior in the transport, and you will see over time also private line emulation coming into the picture. Now, in the most simple term, a segment routed policy only has one candidate path active. It can have multiple candidate paths configured, but only one is always active. With circuit-style segment routing, we change that to say, hey, I actually have two pre-programmed in the data plane. Only one is carrying the traffic, and the second one is there if there is a failure. And with that, we get end-to-end path protection, right? Now, why is this important? And this protection, I think, has a fundamental relationship to how you deal with bandwidth. And I think the protection paradigm is also one of the sources of concerns of people if a packet network can actually give me the bandwidth. Why do I say that? In packet networks, typically we do local protection using some kind of mechanism, for example, MPLS-TE FRR or segment routing loop-free alternate. What do they have in common? We protect a particular interface. So everything that's on that interface, in case of that interface failing, will get sent onto some kind of detour, backup, whatever path. Call it whatever you want, right? In case of TFRR, we're going to send it on the other side of the failed link. In case of TILFA, or topology independent loop-free alternate, we're going to send it on what we call the post-convergence path. You see, we're not going back to the other side of the link. We're going kind of around the link, but then on the shortest path to the destination. What's the problem with that? Protection time, no problem. Sub 50 millisecond, everybody is happy. But we send traffic on some links where we could not reserve or manage the bandwidth beforehand, right? I need to actually plan for those failures, right? That's where planning tools come into the picture, and you run through failure analysis, but you don't really have a priori way of saying, in case of normal operation, my traffic flows this path, and in case of failure, the traffic flows here, and for both cases, I manage and keep track of the bandwidth. With end-to-end path protection, I don't have that problem, because I know during provisioning time what's my working and what's my protect path. If I keep track of the bandwidth and ensure that the bandwidth is not oversubscribed, I'm good, right? And this is, I think, if you ask me personally, one of the key points where you start, putting pieces together where you can actually say, I can run an IP network really like an optical connection-oriented network. Now, granted, we didn't want to do that for the many years, and I would not do this paradigm for many, many low-speed circuits, right? Because what's the, let's say, fundamental problem of end-to-end path protection? You need to switch per path, right? Which means if you have 100 or 1,000 or 10,000 tunnels, right, and you impact them and you need to switch them, you need to do hundreds and thousands and switching operations, right? And each switching operation takes some time, so you will see a linear degrade in terms of switching performance, right? So you only want to do that for a considerable amount of circuits, right? If the circuits are high capacity, I think there's no problem, but I would not do that. I would not use that paradigm and have a SR policy per DS1 circuit that you emulate. You would need to do some aggregation. There are a couple of other things that we had to change, and I learned that the hard way by working with one of the tier 1 service providers. We initially started changing RSVPT traffic engineering to support the exact same behavior. And one thing that we realized, by nature, an IP network is re-optimizing. If there is a better link, a direct link, it's going to be taken, right? But some operators, or I would say predominantly in the optical transport mentality, it's kind of a set and forget, right? They want the best path at the point in time of provisioning. If something better comes after that, they don't care. They planned it, they provisioned it, and it should be there. Only upon request of the operator, if somebody's saying, I want to optimize something, then they do that. But the network is not allowed to do it dynamically. So we had to change that. Now, segment routing circuit style can allow you to do that easily. As we mentioned, adjacency sits give me a deterministic path, and if I don't recompute the path, nothing is going to happen. The same is for failures, right? Traffic engineering, even classic traffic engineering, end-to-end path protection, will re-optimize the working path. So you switch, then you re-establish a new working, and you switch back. People don't like that, right? So what we had to do is to basically say, A, if something, I always want to stick on my path. If it fails, it means it stays down, right? And if it comes back, we can switch back. We have revertive, non-revertive switching, based on your choice. But if it's down, it stays down. Which then brings me back to the next and last thing about protection and restoration, which I think actually then is a good example of why IP networks are great. If they, by nature, re-optimize, they also, by nature, restore, right? Because if, for example, my protect is down, I can ask the PC, hey, is there still some bandwidth and some path left that can actually restore this service during the double failure scenario? And by configuring a third candidate path in the SR policy that will be calculated by the PC on demand, we can do that. So we had to change the nature of IP to really get the proper protection behavior, we could use the nature of IP to, just like that, get restoration. And I would say, get that from an OTN switch implementation. You can get it, but I heard some of the implementations don't really work. So I think this is where really the power of IP is coming to fruition. Transparency. This is where private line emulation comes into the picture, right? What does a router or switch do with the bits coming in on an Ethernet port? We walk up the IEEE stack, and by the way, if you have sleeping problems, I recommend reading 802.3. It's an amazing document. It has like 500,000 pages. It gets longer and longer, and you really put yourself asleep. I have to say, I'm not sure if this is a good thing. After working on private line emulation for quite a while, I started understanding the document and can read it. Not sure if this is good, but it was an interesting learning for me. What we're doing is essentially we take the zeros and ones, we walk up the stack. At some point, there is the PCS layer where we talk about 66, 64-bit encodings, right? At some point, we start understanding frames, and we look at destination MAC address and blah, 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 and VLANs, right? And then we do a layer 2 or layer 3 lookup, where the problem starts with Ethernet pseudowires. Ethernet pseudowires are great, right? But there is always a problem in terms of the control protocol transparency, right? Like, thanks to Metro Ethernet Forum, a lot of the problems got solved. We have specifications, they're all great. Most vendors, including us, have basically done a good job in slowly getting all of this supported, but there's always something missing. For example, MACsec, something that's very famous now because we want to encrypt everything. The key exchange protocol used one of those MAC addresses that are only recommended to be passed. Of course, vendors, including us, initially sucked up those frames, and then you couldn't establish MACsec over an Ethernet pseudowire. Again, that is fixed, at least on our side. I think also mostly the other vendors did it. But just an example, if you are frame and packet aware, you may run into issues. And when you are completely transparent, you don't run into that issue at any time. And private line emulation gives you that. We take the bits, and we put them into packets. It's based on existing concepts we used for emulating PDH and SONET, and we basically took the learnings from that and just defined the technology now for high-speed interfaces. And with that, going back to an Ethernet port, the zeros and ones come in, we stop at the PCS layer. So for private line emulation, Ethernet frames don't exist. All we see is 66-bit code words, and we take them and put them in packets, send them across. With this, we don't understand what a control frame is or a data frame, so we don't really have any of those issues. Now, this requires some specific hardware. We need an FPGA to do the bit and packet conversion, and that adds cost, right? So I was kind of blaming the OTN switches to waste money by putting OTN framers. We kind of do the same with PLE, but the big difference is we only put the more expensive stuff where we need it at the end of the network. In between, you have an IP or MPLS network. Nothing changes, right? So to some extent, if you look at that from an end-to-end perspective, we are again optimizing the cost, maintaining the transparency. Now, next on our top chart is performance monitoring. Now, performance monitoring in the optical world is the holy grail, right? OEM and PM, everybody is very, very adamant about having fancy features there. And there's this classical error second, severely error second, unavailable seconds. You have your 15-minute intervals and 24-minute intervals. So you have a lot of data that is really reported related to parity computation across your TDM frames, right? And you need to do that because if you have impairments on your TDM network, you want to make sure that to understand, is some of my frame mingled because there was some error? And forward error correction at the optical layer could not correct that, and basically the errors are populating up in the electrical domain. This is something that in the packet world we don't really have, right? I mean, we have Y7 and 31, right? We can send synthetic loss measurement probes at a certain rate, and then measure, okay, we have lost so many packets, whatnot, right? Now, interesting enough, I'm not sure how many people are aware of that, but there is a standard from ITU called Y1563 that actually attempts to show you or provide you something similar, a severely errored second Ethernet, right? It's basically a second where you have a high frame loss or packet loss considering your synthetic probes that you have sent. And then, of course, you can also do unavailable seconds. Now, this is not something we have generally in the routers, but probably you don't need, but in your management system, you can calculate that if you want. Now, by actually using private line emulation to give you transparency, but because we also give, add a control word in the overhead, and in that control word we have sequence numbers, we also can give, with private line emulation, some, I would say, fancy and TDM-ish performance monitoring as well. Because we can, from the data that is being sent, correctly understand whether we lost a packet or not. And did we lose too many packets? We declare them severely errored seconds and so on and so forth. So we have somewhat, if you look at this picture and this picture, they're fairly similar, right? The only difference is, in this case, we talk about parity bit errors, and here we talk about PLE packets lost, right? But because we actually put some extra effort on the end of the network outside the MPU, we have the ability to look at sequence numbers, which is something unique, and normally a router doesn't do. Okay. OEM. So IP networks are really cool. They find the best path and send packets across without anything special. They are not really, ideal to do fault isolation or localization on a per service, right? So what are we mostly worried about? In an OTN network, typically, if a client port fails, you want to have in the overhead what we call client signal failure indication, right? Which on the other side will trigger the port to go down or basically be alarmed with, for example, local fault if we talk about an Ethernet client. How do we do that in the packet world? Well, in PLE, we can do that very easily. I mentioned the, actually there is a, I think we have a, there is the control word and the sequence number we talked about, and we have two bits, L and the R bit. The L bit is the equivalent of client signal failure. If we have actually a port that is being down, we still continue to send packets, right? So we start, actually private line emulation, I didn't mention that. As soon as you provision the service, we are sending the traffic, right? So everything is, up and running and provisioned, right? And by doing so, we can actually indicate that the port is down by setting the L bits. And when we set that, the far end can look at the packets and inject a local fault or AIS, right? It also can, of course, if we have severe packet loss, do the local fault as well, because the node detected, hey, the circuit doesn't get any packets. That seems to be the case. We have to have something in the network, and it can inject the fault as well. So long story short, in a PLE network, if you have a client failure, you set the L bits, and you inject the LF, the local fault. Why is this important? Well, if something happens in the network, you typically want to have another overhead signal. And this is the AIS, the downstream alarm indication signal, right? It will lead to the same result. The local fault will be injected. But in the network, you now know, oh, that fault at the customer port is injected because something goes on in my network. And previously, we brought down the port or alarmed the port because there was something going on the customer side. And in PLE, we can do the same thing. And I apologize for mingling up the order here. But if the egress node detects that we have continuous loss of packets, it will go into a packet loss state and will bring down the port as well. So long story short, what I'm trying to show you here is that the gray network, the OTN network, behaves a certain way, and the packet network behaves more or less the same way as well. It's just that you have different mechanisms to indicate what's going on. Now, in preparing, I found actually something interesting. Well, actually, this one I knew already, but there was another one that I will tell you that you may not know. If you just have an Ethernet pseudowire, EVPN pseudowire, for example, right? How does this work, right? Actually, it works there as well, but we are using different things. If, for example, the attachment circuit is down, what we're going to do is we're going to withdraw the route, the BGP route, and then there is a feature called failure propagation, blah, something, I don't know. It's a command that you have to turn on. So if you withdraw the route, then you will actually inject, you will disable the laser, which will basically tell the client a loss of signal. So basically, even though your network here in the middle is still fine, you can propagate the fault very much like the TDM network would do. If you lose the connectivity in the packet network, something similar would happen. Basically, if the next hop of the peer router is not reachable, meaning I also have a circuit down, the TX disable function will also be coming to effect, and we will bring down the client port. There are some show commands and config for you. Actually, there is propagate remote status. That is the command, and that's I think the feature is also called something like that. I didn't know, and I think it was only recently added. A very similar function is also available if you run CFM or Y1731. And basically the same thing would happen. If the client port goes down, 1731 would inject a client signal failure PDU, and that would make you disable the port. And if you have a loss in the network, you would have a timeout, and the timeout would also disable the laser. So essentially what I'm trying to say here in a lot of words and a lot of slides, again, the packet network can lead to the same behavior that the TDM network would give you. And again, here, some example output and configuration. Okay. 2 more to go. Security. That's a short one. So I have come across a lot of, not all, certain requests and that basically, hey, OTN is allowing me to encrypt the ODU payload, and I want to have that same functionality because I'm able to give an encrypted service to a customer. Now, in this case, I think we have still some work to do, right? Now, of course, in a packet network, if something leaves the house, you can use MACsec on your router to encrypt your traffic, right? So I would actually argue, me as an enterprise customer, would I buy a service from the provider that encrypts my traffic, or would I actually encrypt the traffic myself on the router? I mean, it's a question of what router you use, but I think MACsec becomes pretty much, abundantly available, so it's definitely a choice. Obviously, in packet networks, you could say, well, maybe the operator is saying, hey, I'm running your service on a sequence of encrypted links. And actually, segment routing, path computation allows you to do something here as well that helps you. We can actually, for example, create a flexible algorithm or limit the path computation to only include encrypted links, right? Because you can give links an affinity, for example, or you map just certain links that are encrypted in a flexible algorithm, and by nature, you're limiting the traffic to be in the encrypted domain. Now, what I'm really bullish about, and this is future, right? But as we move to IP-based pseudowires, SRv6, is something that that's available for Ethernet pseudowires. We're also looking at that for using it for PLE. Once you have an IP packet, you can use IPsec for encryption. And back to the innovation that has happened or is happening in the ASICs, those high-speed ASICs now also start doing hardware encryption, right? So you will see over time more and more capabilities. So I think actually this encryption topic will also be getting a big, bold green check mark.
Question for you.
Mm-hmm. Good question. So the question is this WAN MACsec? I didn't specifically call out anything here. I mean, there's 2 things, right? Either you encrypt everything, or I think what we used to call WAN MACsec is when you have the VLAN in the clear, right? And that allows you to have multiple of those MACsec lines going from one location to multiple, right? So it could be either or. Yeah.
How future is that last one?
Enough future that I'm not allowed to talk about. So, I mean, yeah.
And the pseudo-wire can still be rerouted and whatnot in
Yeah.
the middle. Okay.
Yeah. I mean, there used to be something for MPLS. I mean, there is some ITF draft out there, and I think some other vendor has implemented something. But with MPLS, it gets a bit more tricky, right? But for IPv6 or SRv6-based pseudo-wires, you just put the ESP and the extension head and the authentication head, and you're done, right? It's much simpler, right? Okay. Last one, spectral efficiency. And this goes a little bit into, I think it's a little similar to the one with latency, right? You try to optimize something in the optical network, and one thing that you want to optimize is the spectral capacity, the spectral usage, right? So you may put a 400 gig wave in a 75 gigahertz grid, right? By increasing the baud rate, I can get more out of my wavelength. So I could potentially have 800 gig per wave, right? But my signal gets broader, right? And essentially in the optical domain, right, we always play with baud rate, the distance we can go, and the data rate we want to carry, right? And those three parameters, you can do many, many different things. And by the way, just I hope I get the point across. This is not trying to be an all-encompassing, description here. But what I'm trying to get across here, well, if you have a higher quality, laser, for example, or for example, a transponder, you could say, well, maybe by actually reducing the baud rate, because I have some more fancy encoding, I can squeeze those 800 gig wavelengths, not in totally 475 gigahertz, aka 300 gigahertz, but maybe only in 225, right? So I invest more money in some big honking transponder, or I'm buying the pluggable from this vendor versus the other vendor, and I'm basically getting more stuff out of my spectrum. What I'm trying to, though, say is that's one part of the story. But if you think about, you have your photonic layer, you have your packet network that you use for packet services, and then you have your private lines. And maybe you have like a 400 gig web scale customer that comes to you as an operator. You give him a wave, fine, right? But then you have a bunch of other ones, and you have muxponders, you use maybe 100 gig wave, and you provision 2 or 3 10 gigs, right? You end up potentially having some of those waves being underutilized. And then you have some waves there that you use to interconnect your packets, or your routers. So what is if you use private line emulation, and those somewhat fairly small private lines can actually easily fit into the unused packet capacity, right? We're actually saving 2 waves, 33%, right? I'm not debating about if the customer wants what you can carry in a wave, give him a wave, right? But as soon as the customer rate is considerably smaller than the wave capacity you provision, I think actually, consolidating that onto the same technology may actually make perfect sense. In summary, I think what I'm trying to get across, and hopefully this presentation was entertaining and informational for you, I'm really trying to give you on the road that I think IP and MPLS networks run in a specific way. By the way, when you run that in a specific way, it's on a per traffic behavior, right? So you can still run the other traffic oversubscribed in a different way, right? One network can give you the behavior you need, right? I think it makes IP MPLS the universal switching and aggregation layer in the network, right? Which I think optimizes a lot of your capacity on the fiber. You can use emulation to solve transparency, right? I don't think PLE will solve world hunger, but what I wanted to make sure is that we can provide a solution. If you need transparency, you have a solution. If you don't care about transparency, don't use it, right? And one thing that I learned, going into the nitty-gritty details of a feature of a certain technology and arguing about this being not available here or there, is not really the problem that I think needs to be discussed. For me, it's all about the network behavior And different technologies use different things to achieve a behavior. But in the end of the day, if you provide the behavior, I think you have solved the problem. So really, I would say things have changed, right? Silicon evolved in the packet network very rapidly. We have nice, cool, coherent optics. And we actually have seen proof points from some industry analysis that actually what used to be the coolest kid on the block called OTN switching may no longer be the coolest kid on the block. And if that is the case, maybe it's time for something new. And with that, thank you very much for sticking through the 60 minutes. Thank you very much for coming. And appreciate you being here, and have a rest of the good show. And if there are any questions, please come to me. Thank you.